Hello guys, I'm sorry I cannot be in class today, so I made some video notes for you. Today's stuff is hopefully fairly straightforward. It's really just like notation and like symbols and classifying numbers into different sets. So with that being said, let's get started. These are the notes I would have done in class today. So if you want to get out a sheet of paper and follow along with me, that would be great. This was kind of a last minute meeting that they told me about, so if I ever have to do this in the future, it probably won't be as, I don't know, just orderly as this may be. So anyway, all numbers are considered real numbers, so I'm actually going to start down here. This is basically every single number, whether it's a whole number, whether it has a decimal, whether it's a fraction, any number is a real number. Whether it's rational, whether it's real. So this is every single number we call real numbers. And on the next slide, I have an organizer that may be beneficial to kind of get a picture of the way that these numbers are all related. A natural number is, the way I remember it, is basically it's a counting number. So it's anything you can count, and we can't count zero things. And we can't count negative things. So it starts at 1. So it's like 1, 2, 3, 4, and so on. There's no decimals attached to that because we technically cannot count a decimal of a thing. So natural numbers are just anything you can count. 1, 2, 3, 4. A whole number is essentially a counting number, but it's including 0. And you guys have talked about whole numbers your entire life. So a whole number is the counting numbers plus the addition of 0. So 0, 1, 2, 3, and 4. So if you're talking about a group of numbers and it's also going to include 0, you have to be more specific and say it's a whole number set, not a natural number set. So that's the only difference between whole numbers and natural numbers. An integer is basically a natural number and their negative values. So for instance, we could say -4, -3, -2, 1, 2. All of these are considered integers. So if you're including negative values, you have to say it's an integer. It's not a natural number, it's an integer. A rational number can be a whole number or a natural number, but it also refers to any decimal or fraction that ends or repeats. So I like to refer to them as like the pretty decimals or pretty fractions. So it's a whole number, a natural number, or any decimal or fraction that ends. And when I mean ends, I mean like 0.5, 0.75, or repeats. Something like, sorry about that, like 1.333, something like that. Or it has a nice pattern, maybe like 1.5757, whatever the case may be. So a rational number is, again, it can be a whole number, it can be 2, but it also includes a decimal or fraction that ends or that repeats. And then the last one is what I like to refer to as the ugly decimals, essentially. They're the ones that do not end or repeat. So it's decimals or fractions that do not end or repeat. And I just spelled that wrong. So like the square root of 3 or pi, stuff like that, that's an irrational number. Do not automatically think every square root is irrational. They'll try to trick you and maybe write like the square root of 4. Well, that looks like it's going to be an irrational number, but we all know that's just 2. So you would say it's a natural number or a whole number, and of course it's a real number. So again, the rational numbers are the prettier decimals. They end or they repeat in a nice pattern. The irrational numbers are the ones that do not end or repeat, and something like the square root of 3 or pi would be a good example for that. So those are the classifications we're going to discuss in here. And then this was just a visual for my visual people to kind of see how they all relate. So everything is a real number. And then from there, they're either rational or irrational. If it's irrational, it is what it is. It's an irrational number. But if it's rational, it can be an integer, which remember is our negative and positive whole numbers. It can be a whole number, which includes 0, or it could be a natural number, which is just our counting numbers, 1, 2, 3, and 4. So they're all considered real, but if you're talking about a square root or pi, it's irrational. Otherwise, it falls into one of these categories. So that's kind of how they all relate. So that's all the classifications. The rest of this is all based on notation, and some of it includes using those different set classifications within the notation. You've probably learned about what I'm about to show you in Algebra 2. When you have a bracket, you're going to use that when you do not want, or when you want to include the value. So when you see less than or equal to or greater than or equal to. You're going to use just the parenthesis when you don't want to include the value, and you always use it for infinity. So you're going to kind of have to bear with me here because I'm writing with my mouse. But for x is less than 4, so I don't want to include the value of 4. So for anything less than 4, it's going to go on forever to negative infinity. So for infinity, I always use the parenthesis. Well, this could get ugly. To negative infinity, comma, and I'm going to go all the way to 4. And then I just close it with a parenthesis. I don't want to include 4. That's why I don't use the bracket. So that's how I could write the interval notation for this. For x is less than or equal to 4, same kind of thing. I'm talking about all numbers that are less than or equal to 4. So it's going to go all the way down to negative infinity. And this time, though, I want to include 4. So I'd write comma 4 and then the bracket. All right. And then for the last one, it's an inequality. So it's saying that x is greater than 3, but less than or equal to 9. So I'm talking all values that are greater than 3, so that's going to be my ending point there, but less than or equal to 9. And since I see the equal to, I'm going to have to put my bracket there. So that's interval notation. I feel like that should be pretty straightforward. You just have to think when you see the inequalities that, you know, if it says less than, you're going to go all the way to negative infinity. If it says x is greater than a number, you're going to go all the way to positive infinity. That may be the new stuff there. So that is interval notation. And the last thing is called set builder notation. And this is probably something that you haven't seen before. So let me do a couple examples with you. There's some goofy notation in this. So you're always going to follow the same general notation. You're going to put a curly bracket and then whatever variable. In this, they're all x's. But if it would have said y, we would have used y. So you always write, I'm using variable x. Then you use this line, such that, then you write the condition. So what was given? Such that x is less than 4. And then we always put comma, and then x is going to be an element of, and this is a new symbol for you guys, an element of, well, if x is going to be less than 4, I don't care if it's a whole number, I don't care if it's a decimal, it can go into the negatives, it can go, you know, some's going to be positive. So think about any value less than 4. That can fit under a rational number, a whole number, a natural number, an integer, so it could be anything. So because it encompasses so much, you just say it's a real number. And I'm going to use the notation that you saw on the first slide. So you may need to go back. That means R. And I kind of probably didn't say that enough. Oh, shoot, I didn't even write them. That's my fault. Okay, let me go back here. There is some notation instead of writing real number out. So you could, for a natural number, you see it written like this. You do 2 lines and then an N. So that lets people know I'm not talking about a variable N, I'm talking about a natural number. Same kind of thing with a whole number. You draw 2 lines and then you make your W. That's ridiculous, but you should draw 2 lines and then W. what else? An integer, we draw 2 lines for our z here. And again, that's not the prettiest thing ever. The 2 lines, third time's the charm maybe, and then make your z. Okay, so that would be an integer. For a rational number, we call that q, which, in case you're wondering why q, it stands for quotient, because this is our fractions and our decimals, so division. You just draw 2 lines on your q instead of just 1, and that's rational number. A real number, just like I was just doing, you're going to draw the 2 lines and then make an r. And then the last one is irrational, and it's just 2 lines like that. So that's the symbols in a nutshell. So you may need to go back and add those. Sorry about that. Okay, so it's going to be any number that's a real number. So I just say it's in an element of real numbers. And so that's how you would do that one. This one's fairly similar. We would write the same thing, but less than or equal to. So I'm going to skip that one and move to this one, even though it is very similar as well. So same thing, you're going to make your curly bracket, much better than I just did with the mouse. You write your variable, which is x again, such that this time they're telling me that x is greater than 3, but less than or equal to 9. That's my condition. So since I know it's in between 3 and 9, it could be a whole number or a rational number or an irrational number. So I just say, because that in between 3 and 9, there are decimals. So again, I just say it's a real number, and I use my notation and then close it. You use this real number most of the time, especially when there's inequalities. You're going to see where I don't use a real number, but most of the time you say it's an element of a real number. All right, let's just try a couple more. So this one says, write the set builder notation for each of the following. And notice here it says -4, -2, 0, 2, 4, and 6. So I'm going up by 2s, or it's talking about going by a multiple of 2. So here's how you could write that. You would say, use whatever letter you want. My brackets are absolutely horrible today. Maybe I'll type the beginning out. Let's do that. Okay, so you could use any variable. I'm just going to use x. What's happening? So x such that x is equal to, think about how you would write a multiple of 2. Like, so it'd be 2 times n, whatever the number is, because 2 times if n was 0, it'd be 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. I could go the other way. 2 times -1 is -2. 2 times -2 is -4, and so on. So that's the condition. So x such that x is going to be equal 2 times whatever n is. And n, to be a multiple of 2, we're not going to have decimals, okay? So it's going to be any integer, because I'm using positive and negative numbers. So remember that an integer is the one that encompasses our negative numbers as well. So n is going to be an element of our integer, so z. So it wasn't a real number this time because I don't want to include the decimals, because that's not going to be my multiple of 2 with my list I have here. So that would be the set builder notation for that one. Then let's see here. Next one, x is less than or equal to -2. So, all right, do my curly bracket. I'm talking about x. So x such that, this time I can just write the condition out, that x is less than or equal to, I'm going to fill that in. And then x, so I'm talking about any value that is less than or equal to -2. So this said less than or equal to. So if we have to think about, okay, what set of elements are those going to be in? So it's anything less than -2. So you could just say it's going to be a real number because it's going to